In this episode, we're going to talk about the normal curve. The standard normal distribution, or normal curve, has a bell-shaped distribution. The area under the normal curve is 1. Since the sum of all probabilities in an experiment equals 1, then for a set of data that is normally distributed, a normal curve is a good way to compute probabilities. In a standard normal distribution, the mean is 0 and the standard deviation is 1. We find areas or probabilities using a normal curve table. In the table, all of the probabilities are computed for you if you have a given z-score. Calculators, Excel, and computer software also compute these probabilities. Notice there are two tables that you can use. One set that has probabilities that are less than 50%, and one table that has probabilities computed greater than 50%. For example, let's say you want to find the probability less than a z-score of 2. You notice that 2 is to the right of the mean. If you want all the probabilities less than 2, then notice that that percentage is going to be greater than 50%. Since the distribution is normal and it's symmetric, with a mean in the center and 3 standard deviations to the right and 3 standard deviations to the left, then 50% of the data is to the left and 50% is to the right. We're trying to find the probability less than 2 standard deviations, so we want all of this region. Notice that this region that we've shaded is greater than 50%, so we're going to look it up on that table. The 2.00 has a value of 0.9772. A z-score is a standard score that indicates how many standard deviation an observation is above or below the mean. For a set of data with a known population mean and a known standard deviation, then we can compute the z-score using the formula z equals x minus the mean over the standard deviation. Thus, the z-score represents the distance between the raw score and the population mean. The z-score is negative when the raw score is below the population mean, and the z-score is positive when the raw score is above the population mean. For example, let's say we know the average age of the students in a particular nursing program. We're told that the mean is 25 with a standard deviation of 3. We want to know the probability that a student in the nursing program is over 30 years old. We know that the mean is 25 with a standard deviation of 3. So if we go over 3, we have 28, 31, 34. And we go back, we get 22, 19, 16. Again, the mean is in the center, 25. In this example, we wanted to find out what's the probability that a given nursing student is over 30 years old. Over 30 years old is this shaded region. Notice that this shaded region is less than 50%. So we find the z-score corresponding to 30. So we have z equals x minus the mean over the standard deviation. So we have z equals 30 minus 25 over the standard deviation, which is 3. So we get a z-score of 5 over 3, which is 1.67. This is the value we're going to look up on the normal curve table. You go down here to 1.6 and across to 0.07. This gives us 0.0475, or 4.75%. Or 4.75% of the students are over 30 in the nursing program. Sometimes we don't have the population mean or standard deviation. In this case, we can get a good estimate by taking a bunch of samples from the population and computing the means of each of those samples. This is called a sampling distribution. The sampling distribution of the mean is the distribution of all of the sample means of the same size n taken from the same population. In a sampling distribution, the mean of all of the sample means is mu, and the standard deviation of the sample means is the standard deviation of the square root of n. We call this the standard error of the mean. In the central limit theorem, the z-score we use is x bar minus mu over sigma over the square root of n. The central limit theorem states that if the sample size is large enough, then the distribution of all the sampling means will approximate the normal distribution. This is true even if the original population is not normally distributed. If the original population has a mean of mu and a standard deviation of sigma, then the mean of the sample means will also be mu. But the standard deviation will be sigma over the square root of n, where n is the sample size. According to the central limit theorem, as n gets larger and larger, the distribution becomes more normally distributed. Let's take the example of filling cans of soda. The mean number of ounces on the soda can says 12. And let's say we happen to know that the standard deviation is 0.11 ounces. If we take a sample of 36 cans that have a sample mean of 12.19 ounces, do these results suggest that the soda cans are filled with an amount greater than 12 ounces? In our sample, we have a mean of 12.19. We already know that the population mean of all soda cans is supposed to be 12, with a standard deviation of 0.11. If we compute the z-score, which is x bar minus mu over sigma over the square root of n, we get 12.19 minus 12 over 0.11 over the square root of 36. We get a z-score of 10.36. We know by the empirical rule that 3 standard deviations encompasses, on either side of the mean, encompasses 99.7% of the data. So we know that a z-score of 10.36 is huge. If we're looking at the probability beyond 10.36, on the table we get a value of 0.0001. That's all for now. Try some homework.